In the next two videos, I want to apply what we've learned about integration by substitution to definite integrals. And so it's just going to add one more layer of complexity on top of that, but it's still a very manageable process. So here we have the integral from 0 to 1 of x times the quantity x squared plus 1 to the third. We have function composition. Inside function is x squared plus 1. Its derivative is 2x, which is a constant multiple of the x that shows up on the outside. So we're good to go. And u is equal to x squared plus 1. du is equal to 2x dx. Now I have an x and a dx there, so I still want to divide by 1/2, or multiply by half. So 1/2 du is equal to x dx, and u is equal to x squared plus 1. And so we have gotten rid of all of the x's that are in the integrand. And so that leaves us with 1/2 integral of u to the third du. Now, what we have to understand is that our limits of integration are also in terms of x. So we really should write them as 1/2 integral from x equals 0 to x equals 1 of u to the third du. Now, we can't leave them as x values in there, and so the way we're going to deal with that is to go back to our definition of u equal x squared plus 1 and find out what u is when x is equal to 0 and when x is equal to 1. So when x is equal to 0, u will just be 1. And when x is equal to 1, u will be 2. So instead of integrating on x from 0 to 1, we're going to integrate on u from 1 to 2. And so now we have transformed the original integral into 1/2 integral from 1 to 2 of u to the third du, and we're ready to go. U to the third is u to the fourth over 4, and that's a constant that can come out. And so now we have 1/8, 16 minus 1, and that's equal to 15/8. So what did we do different with a definite integral than we did with an indefinite integral? And the main thing has to do with the limits of integration. Not only do we swap out all the x's for corresponding terms, for corresponding components in terms of u, we're also going to swap out our limits of integration from x values to u values. And we do that by taking our u equals a function of x and then finding out what u is for different values of x. Okay, so now I'd like you to try one of these. Integral from -1 to 2 of x squared times the quantity x cubed plus 1 squared dx. Remember, in addition to swapping out all of your x's for u's, you want to swap out your limits of integration for u values in terms of those x values. And you can stop the video here and work on that, and I'll give you the answer in a few seconds. Okay, so what you should get out of that is a value of 81. If you got that, you can go on to the next video. Otherwise, I will go through the solution to this one now. So we can see in this definite integral, we have function composition. The inside function is x cubed plus 1. Its derivative would be 3x squared, which is a constant multiple of the x squared on the outside. So we're okay to go with this. U is equal to x cubed plus 1. Du is equal to 3x squared dx. Divided by 3, we can isolate the x squared dx. So the x squared dx is 1/3 du. The x cubed plus 1 is u. When x is 2, u would be 9. When x is -1, u would be 0. And so we get 1/3 integral from 0 to 9 of u squared du. U squared is going to become u to the third over 3, bringing the 3 out. We get 1/9 times u to the third from 0 to 9. So 9 to the third is 243, 0 to the third is 0, and 1/9 of 243 is 81. Okay, so that does it for this one. We'll go on to one last set of examples involving integration by substitution with definite integrals in the next video.